We're going to use Newton's laws to analyze a situation where we have two objects that are connected by a rigid cable, where one object is sliding along a table and the other object hanging over the cable is free to move vertically up and down in something we call a modified Atwood machine. And what we're looking for here is to find the acceleration of the blocks and then the tension in the cable that is connecting them. In our case, we have block 1 and block 2. We do have some friction this time between block 1 and the surface. And we're going to assume the cable is rigid, so the tension in the cable up here is the same as the tension in the cable connected to block 2. Now we have to be careful on one little spot before we start working on this. Otherwise, we could run into some trouble. We just want to make sure that the direction of the acceleration for each of our objects is going to be positive. Otherwise, we could run into trouble with signs a little bit later. So for my blue object, I'm going to call up the positive y, and I'm going to call right the positive x. For my red object, I'm going to call down positive y. Now, I know I probably said before you have to be consistent. Well, in our case, as long as you're consistent with each object with your coordinates, you're going to be fine. And here, because what pulleys tend to do is this is going to accelerate to the right, the pulley changes the direction of that acceleration. That string is moving to the right and it's kind of bending around the pulley. So that's why we have to make sure we do this. Otherwise, we're going to run into trouble. But now that we have our coordinate system set, we can draw some free body diagrams and we can write some Newton's second law equations that hopefully we're going to be able to combine in a way that lets us solve for the things we're looking for. So first, let's work on object 2. So we have this tension force going up. We have the weight of object 2 going down, which I'm going to do this in my head really quick, which is going to be its mass times its gravity field constant. So that's going to be 2 times 10 if we assume we're on Earth. So that's going to have a weight of 20 newtons. For our object 1, we have the tension to the right, which is the same tension as the one that's acting on the red. We're going to have its gravity force, which is going to be 100 newtons. Its mass times gravity field constant of 10. It's going to have a normal force acting on it because it is sitting on a surface. And it is sliding across a rough surface, and they give us the coefficient of friction. So it's also going to have a friction force acting on it. Now what we can do is we're going to write our free body diagram, our Newton's second law equations for each of these. So let's start with the blue one. So we have, let's see, some of the forces on object 1 in the x direction is going to be our tension force, because remember I called right positive, minus the friction force, and that's going to equal the mass of 1 times the acceleration. In the y direction, we're going to get the normal force minus the gravity force on object 1, and that's going to equal the mass of object 1 times the acceleration in the y. But it's sliding along just in the x direction, so there is no acceleration in y. So we can set that to 0. And again, this is a situation we see a lot. It's not always true, but I'm going to just quickly solve for this. So the normal force is 100 newtons. In this case, it's equal to the weight of object 1. We can write some equations for the red one. There is no really anything happening in the x direction for the red one, so we're just going to write a y equation. So sum of the forces in the y are on object 2. In the y direction, that's going to be, now again, we're calling down positive for the red one, so it's going to be the weight of the red one, or weight of object 2, minus the tension force, and that's going to be the mass of object 2 times the acceleration. Now this time, object 2 is accelerating in its y direction. And the way we set this up is this acceleration is the same as that acceleration because they're moving together through a rigid cable. And now what happens a lot with these objects is that a way we can solve these, now you could solve these by substitution if you wanted to, because if we look at what we have, we know once we find friction, we will have so we technically have 3 unknown for, if we include our friction equation down here. We have 4 variables for 4 unknowns, but we can find friction pretty easily because you already found a normal force. Then we'll have two variables for two unknowns. So we could solve by substitution. But when you have situations like this where you have multiple objects and there is a force, a Newton's third law force that they're interacting through, in this case, it's the tension. If we add the equations together, it's going to help us. It's going to automatically kind of drop out that force and allow us to solve for something like the acceleration in this case. And then we can go back and use that somewhere else. So again, any situation where you have multiple objects and they have a Newton's third law force, a nice way to help you solve it is to add the Newton's laws equations together, at least the ones that have that similar Newton's third law force in it. And it'll make your life a little bit easier solving. So we'll do that in a second, but let's first find this friction force. So it's going to be the coefficient of friction, which is 0.15, times the weight of object 1, which was 100, because it was equal to the normal force. And that's going to give us a friction force of 15 newtons. So now I'm going to go up and I'm going to add my red equation. Excuse me. Add my y equation for my object number 2. Add it to my x equation for object number 1. We're going to see something nice is going to happen. So we get Fg2 minus tension equals m2 times a. And now we can see if I add these, the positive tension here and the negative tension there are going to cancel each other out, and I get Fg2 minus the friction force equals now m1 and m2 are both multiplied by a, so I can write this as m1 plus m2 times a, and I can see that the acceleration is going to be the difference in the mass 2's weight and the friction force divided by the total mass. So let's just write it that way, and then we'll put some numbers in. Divide both sides by the total mass. And we get our acceleration ends up being, we can pop some numbers in. So we get 20 minus 15 divided by, let's see, the total mass is going to be 10 plus 2. And that gives us 5 over 12, which gives us an acceleration of about 0.42 meters per second per second. Now to find the tension in the cable, we can just go back, use that acceleration in one of our equations. We didn't use our red one, has some space, so we might as well use that. So let's plug our acceleration in there. So let's see, the red weight, or the object 2's weight, is 20 newtons minus the tension force equals the mass of object 2, which is 2, times the acceleration, which we just found to be 0.42. And doing a little bit of algebra, we end up getting that the tension force ends up being a little over 19, so about 19.2 newtons. So a little bit less than the weight of our object number 2.